This video is for Lesson 10-2, Congruence. Learning goals are to determine whether figures are congruent and to specify a sequence of rigid motions that will make a figure map onto a congruent figure. Consider the 5 triangles shown below. These are isosceles triangles. Now some of these are congruent because a series of rigid motions, again those are translations, rotations, and reflections, can map the triangles onto another. If you can find a series of rigid motions that map a triangle onto another, then we know for sure that triangles are exactly the same size and shape, that they are congruent. So number 1, shade all of the figures that appear to be congruent to figure A, and I've shaded those in purple. For example, if we rotate figure A 90 degrees to get it to point downward and then slide it to the right, we could map it right onto this arrow, and that shows that this is exactly the same size and shape as the original. To prove that two figures are congruent, a specific combination of rigid motions must be found that maps each point of one figure to corresponding points of the other figure. Number 2, predict whether the two triangles shown in the figure are congruent and explain. So this triangle and this triangle, yes, I think that they're congruent because they appear to be the same size and shape. Now, how can we confirm our prediction? Well, based on the idea from this lesson, if we can find a series of transformations that would map this triangle onto this triangle, that would be our justification for knowing they're congruent. And so that's what I'm going to do. Find a composition of transformations that maps one triangle onto the other. Question 4, could a single translation, reflection, or rotation work? The answer is no. The triangle would have to be rotated to get it oriented in the correct direction and then slid. There's no way to get that mapped onto that in only one step. Number 5, how could a rotation followed by a translation map one triangle onto the other? So I've labeled this triangle A. This is going to be our first triangle. Let's make it move to where the other triangle is. If we rotate it counterclockwise around the origin, around that point, so if we're turning it this direction, 90 degrees, it would look like this. Then we could translate it upwards to get it to the correct height. So I think if we rotate triangle A 90 degrees counterclockwise around 0, 0, then translate up 5, we could move that triangle onto that triangle. Number 6, propose a composition of a rotation and translation to map the triangle in the first quadrant onto the triangle in the third quadrant. So kind of the reverse of what we just did. This time we're going to think of this as the first triangle. How could we map it to this triangle? We're going to rotate it first to get it to, if we rotate it around the origin, turn, 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 we could get it to land here. Oop, how long is that right there? 4 units. 1, 2, 3, 4. It only goes to there. We could get it to land there. And then do you see how you could slide it to the left 5 spots? So that's what we're filling into this table. Our rotation is going to be around 0, 0, and it's going to be a negative 90 degree rotation, a clockwise rotation. Then our translation will be 5 units to the left. We don't have to move it up or down any. Okay, so when you take the dot at 0, 2 and you perform that rotation, that point will end up at 2, 0. Let me show that to you in the picture. When you take the dot at 0, 2, that corner of the original triangle, and you rotate it 90 degrees, it ends up here at 2, 0. This table is asking us to figure out where all 3 vertices of the triangle end up. And I have found those values and put them in the chart in purple. Then we're doing the translation 5 units to the left. So the x-coordinate is going to be adjusted 5 to the left. And that's where you see these final answers. Number 7, was our prediction correct? Yes, the triangles are congruent. And our reason is because we did find a composition of transformations that mapped one to the other. Okay, use the figure for items 8 through 10. So we have this rhombus and we have this rhombus. Predict whether quadrilaterals ABCD and BEFG are congruent. Well, yes, they appear to be the same shape and size. How could we test this? We need to find a composition of transformations that maps ABCD to BEFG. If we can somehow make this rotate and move until it lands perfectly on top of this, then that's our reason to know that they're congruent. So number 10, follow our plan to test our prediction. Identify the motions that we applied. How about we rotate ABCD 90 degrees counterclockwise around point B. So keep that point fixed and rotate that 90 degrees counterclockwise. Can you imagine that turning in your mind? Can you see it in your mind? Then slide it to the right. Here are some check your understanding questions, so I'll pause the video. Okay, in activity 4, we're now in activity 10. So activity 4 was quite a while ago. We learned another definition of congruent figures. That definition involved the measurements of the sides and angles of a figure. For example, if two triangles have the sides of lengths A, B, and C, then the triangles are congruent. That's saying if there are two triangles and all three sides of one triangle are the same length as the three sides of the other triangle, we knew that those triangles were congruent. That was back in activity 4. Congruency can also be shown when two triangles each have two sides of lengths A and B, and the angle between the two sides is the same in both triangles. So this is another property of congruent triangles, something that is true about congruent triangles. If we have two triangles and two of the sides are the same length, and the angle between those sides are the same, then we know that they're congruent triangles. Line segment A connects points 2, 3, and 5, 3. Line segment B connects points 1, 0, and 1, -6. Question 13. Find a composition of two rigid motions that maps line segment B to line segment B prime so that it overlaps line segment A. There's more than one possible answer. The one that I came up with in the video is to do this. Let's rotate around point 1, 0. So here's 1, 0. We're going to rotate figure B 90 degrees. We're going to take figure B and turn it counterclockwise 90 degrees. It would end up looking like this, stretching over to the 7. Can you visualize that black segment turning a quarter turn counterclockwise and ending up here? Then do this translation, up 3. So this thing is going to move up, slide up 3 spots, and it would land here. It overlaps figure A. Can you see that? And that is called B prime, this one here in brown ink, overlapping figure A. Number 14, what pair of points does line segment B prime connect? Well, in the way that I did this, it connects this point to this point. This is 1, 3, and this is 7, 3. And you see those answers here and here. Number 15, can you add a third rigid motion to this composition? Explain why or why not. Well, I think that I could. Because B prime is overlapping A right now, if we were to reflect B prime over this line right here, which is the perpendicular bisector of B prime, I think that it would kind of just flip over and land back on itself. Can you visualize that? And so it is possible to add one more transformation to our series that we had created there. We could reflect over the line x equals 4. Number 16, in the composition you identified, what subsection of line segment B maps onto line segment A exactly, and what is its length? So line segment B, this original vertical black segment, what part of it is the part that overlaps segment A? And that would go from this spot here, 3 units, to this spot here. It's this chunk of it that ends up as this chunk here, after doing the rotation and then sliding up. And so our answer to this question is the part from 1, -1 to 1, -4, and that's 3 units long. Here's some check your understanding questions, so I'll pause the video. So in this lesson, we figured out whether figures are congruent, and we did that by looking for a transformation or a sequence of transformations that would map one to the other.